Welcome to the deep dive. Today we're digging into something pretty consequential in how we evaluate LLM agents. There's this core finding we need to talk about.
Right.
In a live dynamic financial market setting, the LLMs scoring highest on general reasoning tests, like LMArena, they actually performed worse than models that scored lower.
It's quite a striking result. It really pushes back against this assumption that better general reasoning just automatically means better real-world performance, especially when things get noisy and uncertain.
Exactly. When you throw in live uncertainty, real-time feedback, delays, those static benchmark scores, suddenly they look pretty misleading.
Yeah, they lose their predictive power in that kind of complex environment.
So that's our mission today. A deep technical look at the environment that uncovered this gap LiveTradeBench. It's a new framework designed for evaluating LLM agents doing real-time portfolio management.
And it's built to be rigorous, continuous time, high fidelity.
Absolutely. And look, we're assuming you, our listeners, are already pretty familiar with the ML and financial math side of things. So we're skipping the 101 and jumping straight into the technical design choices, the stuff that makes this benchmark so revealing and, frankly, so tough for the agents.
Okay, so LiveTradeBench really stands on three core pillars that set it apart from, say, older backtesting methods. The first one is fundamental, live data streaming.
This is critical, right?
Absolutely essential. They completely avoided the typical pitfalls of offline backtesting, things like information leakage, looking into the future inadvertently. By using real-time data streams, the agents face genuine uncertainty and get feedback as it happens.
Okay, that makes sense. Pillar 1, real-time data. What's the second?
The second pillar moves beyond simple actions. It's about portfolio management abstraction. We're not talking about an agent just deciding buy Apple or sell Google.
So it's a higher level of strategy.
Exactly. The agent's task is strategic asset allocation across a portfolio of assets. This forces it to think about risk management, correlations between assets, portfolio-level goals like return versus volatility. It's a much more complex reasoning task.
Right, integrating risk is key there. And the third pillar?
The third is multi-market evaluation. They don't just test in one scenario. They use two very different evolving markets, the U.S. stock market and the Polymarket prediction markets.
Why two? What does that give you?
Well, the markets are structurally distinct. The U.S. stock market is mature, regulated, driven more by fundamentals. Polymarket is decentralized, much more about sentiment, narratives, rapid changes. Testing across both really probes the agent's ability to generalize and adapt its strategies.
Okay, that dual setup is clever for testing generalization. Let's dig into the formal setup a bit. They model this as a POMDP, a partially observable Markov decision process. Why that specific framework?
Well, the partially observable part is key. It formally acknowledges that the agent never sees the full, true state of the market. It's always acting with incomplete information, massive uncertainty.
So what does the agent see? What's in that observation? HODLR.
It gets three things. First, its current asset holdings, $220, so how much of each stock or Polymarket contract it holds, plus cash. Second, the latest observable market prices, $2, with timestamps. And third, crucially, contextual signals, $2.
Contextual signals, like news.
Exactly. Real-time news summaries, sentiment analysis, things relevant to the assets it's trading. This textual information is vital, especially in Polymarket.
Okay, holdings, prices, context, and what can the agent do? What's the action space order?
It's actually quite elegant. The agent doesn't output low-level orders. Instead, it outputs a target allocation vector. Think of its percentages. I want 10% in Apple, 5% in Microsoft, 15% in this Polymarket contract, 70% in cash, for example.
And these percentages have to sum to 100%, right?
Correct. And they impose a long-only constraint, so no short selling. All allocations AT must be non-negative and sum to 1. It's a standard portfolio management setup.
So how does that target allocation actually turn into trades? That's the transition dynamics, $2.
Right. There are two parts to the transition. First, the market itself evolves. Prices change, new news comes out, that's exogenous, outside the agent's control. Then, based on the agent's chosen allocation in AT, the system calculates the trades needed to reach that target.
How does that calculation work, roughly?
Basically, the current portfolio carried to dollars is revalued using the new market prices, ADT plus 1. That gives a new total value. Then, that total value is redistributed across the assets according to the target percentages in AT. The difference between the old holdings duelers and the new holdings TT plus 1us represents the trades executed.
Okay, but it sounds like it's abstracting away some real-world complexities, like transaction costs or maybe the price impact of large trades, slippage. Doesn't that limit the realism?
That's a totally fair point, and the paper acknowledges it as a limitation. The justification is that they want to evaluate the LLM's strategic reasoning, its ability to make good high-level allocation decisions based on the available information.
So focusing on the what rather than the how of execution.
Precisely. It treats the LLM like a portfolio manager giving instructions, not a high-frequency trader optimizing execution microsecond by microsecond. It maps the strategic decision dollar directly to the resulting portfolio change, delta Q dollar. It's a simplification, but arguably necessary to isolate and assess the core reasoning capability first.
Okay, I can see the rationale for focusing on strategy. Let's go back to those two different markets. That differentiation seems critical for the results you mentioned earlier.
Absolutely. It's the key to testing generalization. First, you have the U.S. stock market environment. Think mature, regulated, lots of historical data.
Driven by fundamentals, earnings reports, macroeconomic trends.
Exactly. Prices tend to move more smoothly. There are strong correlations between sectors. Success here often rewards careful analysis, diversification, maybe a longer-term view. The portfolio they use is pretty standard. 15 well-known stocks and ETFs like Apple, Microsoft, JP Morgan, ExxonMobil, plus a cash component.
Okay, the traditional finance playground. And the other one,
Poly-
Polymarket.
Yeah, Polymarket's different. It's a decentralized prediction market. Think bets on future events. Will the Fed raise rates by 2025? Will X candidate win?
So binary contracts, yes, no outcome.
Mostly binary contracts, yeah. And it's much more driven by sentiment, news flow, narratives, sometimes rumors. It's volatile. The assets are often loosely coupled. You need rapid adaptation, good event-driven reasoning. Being sensitive to shifting narratives is key.
How does the allocation vector work there if it's yes-no markets?
Good question. For each market, each question, the agent's action vector has two components, one for the IS shares and one for the NO shares. But there's a constraint. The agent has to pick a side. You can only allocate to either WES S or NO for any given question, not both.
Interesting. So it forces a directional bet on each prediction market it enters.
Right. And remember, for both the stock market and Polymarket, the agent is always getting that same three-part observation. Its current positions, the market prices, and that crucial context stream with the news and sentiment.
Okay, let's peek inside the agent now. How does it actually make these allocation decisions? It's got a policy that takes the observation and its memory to output the allocation hacking.
Right. The architecture they use is based on the React framework reasoning and acting. It's designed to be somewhat interpretable, which is helpful. It has a few key components.
Like what?
First, there's tool use. This isn't just about, calling an API. It's about processing the raw inputs, taking the stream of prices and calculating volatility features, for example, or taking raw news headlines and summaries and extracting the key entities or sentiment. It structures the chaos.
So turning raw data into useful features, till do it. Makes sense. What else?
Memory, WA. Since trading is a continuous process, the agent can't just react to the latest tick. It needs historical context. So it maintains a memory buffer, typically a fixed-length sequence of recent observations.
Giving it some sense of trends or recent events?
Exactly. And the core is the reasoning step. Using the React approach, the LLM doesn't just jump to an action. It generates intermediate thoughts. It might say, okay, observed high volatility in tech stocks, news mentions potential regulation, my current tech exposure is high, maybe I should reduce risk. It verbalizes a chain of thought.
So you can actually see its rationale to some extent.
Yes, that's the goal. It interprets signals, maybe recalls similar past situations from its memory, hypothesizes about potential outcomes, and then it outputs the final allocation vector against dollars. This provides valuable interpretability.
Okay, so we have this agent architecture running in these two markets. How do they actually evaluate performance? They ran this live for 50 days, right? With 21 different LLMs.
That's right. A pretty extensive live test from August 18th to October 24th, 2025. And they didn't just look at profit. They used a standard set of financial metrics.
Let's quickly recap those.
Sure. Cumulative return, CR, is the obvious one, total growth over the period. But that's only half the story. You need risk metrics.
Right, like volatility, how much the portfolio value bounces around.
Exactly. And maximum drawdown, MDD. This one's critical in finance. It measures the largest peak-to-trough drop in portfolio value. How much did you lose during the worst period? Preventing catastrophic losses is often paramount.
So MDD captures the downside risk and the overall measure.
The Sharpe ratio. This is the classic risk-adjusted return metric. It tells you how much return you generated for each unit of risk you took, measured by volatility. A higher Sharpe ratio is generally better and more efficient returns. Oh, and they also looked at win rate, WR, the percentage of periods with positive returns.
Okay, CR, volatility, MDB, Sharpe ratio, standard metrics. Now let's get back to the surprising main findings. The first one you mentioned was this general capability gap.
Yes. This is where it gets really interesting. You'd expect models that are generally smarter or better at reasoning, according to benchmarks like LMArena, to also be better traders, right?
Intuitively, yes.
Well, the data says no. The Spearman correlation, which measures rank correlation between LMArena scores and cumulative return in the U.S. stock market, was just 0.054, basically zero relationship.
Wow. So general smarts didn't translate to stock market profits at all. What about Polymarket?
It gets even stranger. In Polymarket, the correlation was negative 0.38.
Negative. So the higher the general reasoning score, the worse the agent performed in the prediction market.
That's what the data suggests.
Yeah.
It's a pretty stunning finding. It implies that whatever skills LMArena measures might actually be counterproductive in that fast-paced, sentiment-driven environment. Maybe slow, deep deliberation hurts you there.
That really undermines the idea of just scaling up general abilities for specialized tasks, which leads to the second main finding, lack of generalization.
Exactly. Success in one market didn't predict success in the other. The correlation between the Sharpe ratios achieved in the stock market versus Polymarket was near zero.
Can you give a concrete example of an agent showing this?
Sure. Take GPT 4.1. In the stock market environment, it was the top performer, achieving over 6% cumulative return. A real star.
Okay, so it should ace Polymarket too, right?
In Polymarket, its cumulative return was worse than netted of 30%. A massive loss.
Minus 30%. What happened?
The analysis suggests its trading style, which worked well in the relatively smoother stock market, was just too sensitive, too reactive for Polymarket. It made large, frequent allocation changes based on noise, perhaps, leading to significant losses in that high volatility environment.
So the strategy wasn't robust across market types. Did they observe consistent strategies or styles within each market, though?
That's a third finding, right? Distinct portfolio styles. Yes, definitely. You can see clear patterns. Some models adopted conservative styles. Claude Opus 4.1 and Grok 4, for instance, generally had lower volatility and smaller maximum drawdowns. They seem to prioritize not losing money.
Protecting capital. Makes sense. Who are the risk takers?
On the other end, models like Kimi K2 Instruct and GPT-5 seemed willing to accept much higher volatility, presumably chasing higher returns, and you saw structural differences too.
Like how they built their portfolios.
Yeah. For example, GPT-4o tended to concentrate its investments in just a few big tech names: Apple, Microsoft, NVIDIA, highly concentrated bets. GPT-5, in contrast, tended to diversify more broadly across the available stocks.
Interesting. Any other style differences?
Cash management was another one. Llama 4 Scout consistently held a large cash position, often over 20% of its portfolio. Very cautious. GPT-5, on the other hand, stayed almost fully invested, keeping its cash ratio below 10%. Different risk postures.
What about those models specifically designed for complex reasoning, like DeepSeek R1? Did their advanced reasoning capabilities lead to better, more stable performance?
You might expect that, but actually no. Models like DeepSeek R1 and Qwen 3 Thinking, which are explicitly built for sophisticated reasoning, showed substantially higher volatility, especially in Polymarket, sometimes over a 140.
Higher volatility. Why would better reasoning lead to more erratic performance?
It's counterintuitive, right? One hypothesis is that in a noisy, fast-moving environment, maybe too much deliberation, overthinking every little signal can actually degrade performance. It might lead to inconsistent actions or overfitting to noise, whereas a simpler, more decisive heuristic might perform better.
So excessive thinking could be a detriment in some contexts.
Fascinating.
Okay, they also did some more advanced analysis to really probe what was going on, like testing if the agents were just making random moves.
Right, the rolling delta analysis.
Yeah.
This was designed specifically to check if the agent's decisions were actually dependent on current market information or if they were just guessing.
How did they test that?
The idea is simple. What happens if you force the agent to use an old decision? They compared the agent's actual performance, CSAR Taller, with its performance if it had been forced to hold the same portfolio it held days ago, the CRTR. If the decisions rely on timely information, performance should get worse as dollar increases, meaning Deltac CR dollar should be negative.
And was it?
Yes. Performance consistently degraded as colored dollars got larger. In Polymarket, for example, delaying the action by using an older portfolio state resulted in about a 2% drop in cumulative return. This confirms the agents weren't just acting randomly. Their decisions were responsive to contemporaneous market signals.
Okay, so they are reacting to live info. And those reasoning traces you mentioned earlier from the React framework, what did they reveal about which information the agents were focusing on?
This was really revealing. They analyzed which input source position, price history, or news context was most frequently cited in the LLM's generated thoughts.
And the winner was?
News context, $T, by a large margin. It was referenced in the reasoning traces 74.1% of the time for stock market decisions, and even higher, 82.6% of the time for Polymarket decisions.
Wow, over 80% in Polymarket. Price history was secondary.
Yes, price history was cited, but less frequently than news. Current position information was cited least often. This really underscores the importance of that contextual news feed, especially for the sentiment-driven Polymarket. The challenge isn't just technical analysis of prices, it's interpreting qualitative, unstructured information flow.
Let's make this more concrete with the case studies. Can you walk us through the U.S. stock cash dynamics example?
Sure. This highlights how agents used cash as a risk management tool. Around August 28th, there was a rally, particularly in tech stocks. What did the agents do? On average, their cash allocation dropped significantly, from about 17% down to 7.5%.
So they deployed capital to participate in the rally.
Exactly. And the reasoning traces confirm this. GPT 4.1, for instance, explicitly mentioned positive market sentiment and its decision to increase exposure to tech growth stocks like Meta, Apple, and Microsoft.
What about the opposite scenario, a downturn?
On October 10th, there was a sharp market drawdown. Here, the agents reacted defensively. They rapidly increased their cash holdings. Gemini 2.5 Pro, for example, boosted its cash allocation from 25% up to 35% during that period.
And did that help?
Yes. The agents that increased cash most aggressively generally experienced the smallest losses on that difficult day. It shows they were capable of using cash dynamically as a risk mitigation strategy, not just holding a static amount.
Okay, so sensible risk management in the stock market. How did things look in the Polymarket news sensitivity case? This was the Russia x-Ukraine ceasefire in 2025 market.
Right. This case really illustrates the signal versus noise problem in Polymarket. On October 13th, some news reports surfaced things involving Zelensky, Gaza, Trump that seemed vaguely optimistic about a ceasefire.
Vaguely optimistic, not decisive.
Exactly. The news wasn't concrete. But several agents reacted strongly, executing large portfolio switches, abruptly increasing their allocation to the yes side of the ceasefire market.
And did the market move? Did they profit?
Nope. The market price barely budged. The news was essentially noise, and the agent's overreaction yielded no profit. It shows the danger of reacting too quickly to ambiguous information.
But then later, there was more impactful news.
Yes. On October 17th, there was credible, high-impact news. Zelensky visited the White House. This was seen as genuinely significant for the prospects of continued support, making a near-term ceasefire less likely, perhaps, or changing the dynamics somehow relevant to the contract.
How did the agents react this time?
Here they showed more strategic stability. They interpreted the news as significant, strengthened their existing positions accordingly, likely moving more towards no or adjusting based on their interpretation, and held them. As the Polymarket price did react steadily to this real news, the agents who positioned correctly captured tangible profits.
So the key difference was distinguishing credible, impactful signals from the background noise and reacting proportionally.
Precisely. That ability to weigh the significance and credibility of qualitative news seems absolutely critical for success in these kinds of decentralized, narrative-driven markets, and it's clearly a major challenge for current LLMs.
Okay, so stepping back, LiveTradeBench seems to have achieved its goal. It's provided this unique, continuous environment to really study how LLMs perceive, reason, and act under live uncertainty. And in doing so, it starkly revealed the gap between static test scores and real-world financial competence.
Absolutely. It lays a foundation. And importantly, the authors are very upfront about the current limitations, which really point the way towards future research.
Right. Let's touch on those. They mentioned 3 key areas. First, market frictions.
Yeah, this is a big one. The current setup ignores transaction costs, slippage, the price moving against you as you trade, and liquidity constraints, not being able to trade large sizes easily. Including these would make the simulation much tougher and the reported returns likely lower, especially for agents that trade very frequently.
Okay, adding friction is a necessary next step for realism. Second limitation.
The observation and action space.
Yeah.
Right now, because of the limited context windows of LLMs, the amount of historical data the agent can consider is restricted. News inputs have to be summaries, not full articles. And the number of assets they can manage simultaneously is also limited. Expanding this is crucial.
More history, deeper context, wider asset scope. Got it. And the third limitation.
Agent design. The React architecture used is relatively basic. Future work needs to explore more sophisticated agent designs. Think about integrating specialized financial analysis tools, maybe hierarchical memory structures to handle different timescales, and definitely using advanced reinforcement learning techniques to actually train agents to develop adaptive trading policies within the environment.
So lots of room for improvement in the agent's capabilities and the environment's fidelity.
For sure. It's just the beginning. But if we circle back to that really provocative finding the negative correlation between LMArena scores and Polymarket performance,
Yeah, that general reasoning ability seemed to actively hurt performance there.
it leaves us with a really interesting question for the field, right? If general language mastery and perhaps deep deliberation are actually anti-correlated with success in these fast, noisy, sentiment-driven environments, what is the crucial capability we need to build into these agents? It might not be just better language understanding.
What else could it be?
Well, perhaps it's something different. Maybe a specific kind of analytical capacity, or perhaps even an engineered form of, say, probabilistic reasoning, knowing when not to act, or a better ability to assess information credibility rapidly. Something beyond just being able to reason broadly or generate fluent text. How do we build models that can navigate qualitative uncertainty and distinguish signal from noise without just reacting to everything? That feels like a key challenge highlighted by this work.